Bismillah ar-Rahman ar-Rahim. Good evening, guys. Let's finish the last lecture. It was about how we can determine some application of CRO. What is the CRO? The C from cathode, R from ray, oscilloscope from O from oscilloscope. Our job today to determine some applications to this device. It's a widely common device in medical devices and in another department. And after that, we will try, or let me say, we have another purpose, the specific purpose today to determine the sensitivity, deflection sensitivity to this device at DC and AC. Okay, at first, let's take a simple idea, general idea about what is the CRO, how we can use it, how this device works. Okay, at first, the purpose, like I said before, to demonstrate the many application of the cathode ray oscilloscope. Like I said before, cathode, C from cathode, R from ray, oscilloscope from O. Let's take idea about the introduction of this device. The CRO is a widely used lab tool to measure voltage signals. By use it, we can take voltage signals from a lot of frequencies, a lot of waves, because it's one of its advantages and make it be unique correctly across a wide range of frequencies, like I said before, and that will be at specific time. By that, many measurements are made easier by using it. It has another advantage. These advantages are stability, easy, and reliability operation. Let me say the alternating voltage in our houses in these days, it's not stability. Why? We can check that from the calculator, from the small voltmeter in any protect electric device connected with refrigerator, television, I don't know. You can take a look. The voltage will be less than 220, and after that, at some moment, will be more than. That's mean this different potential is not stability. It's reverse with this device. The readings, the recordings, not recordings, let me say the readings, the waveforms from this device will be stability with one result. Now let's take about why we take it at the electricity department. Because here we have some link in a generally medical department with this device. We have some generally link with this device. Actually, on several medical devices using the CRO to display the physiological waveforms. It's necessary, it's helpful to can plot the physiological waveforms by using it instead of paper and consuming some papers, money, something like that. And at the same time, it has another many uses, such as medical device project management, clinical data and study management, research education, and at last, device development planning. I selected that from Google, but if you search more, you will use another uses to this device. Now let's take a deeper look to this device, how this device can work. Actually, let's focus on its heart. Its heart is the cathode ray tube. What that mean? Let's take an idea, let's think about that. How the screen can emit these lines or waves to us and what that's equal to us. The heart to the cathode ray oscilloscope is the cathode ray tube, like we are saying here. Actually, let me simplify these words. When the cathode take the current, the cathode will produce electrons, okay? And we have near from the cathode, the heater. The heater job to increase the temperature to these electrons. By that, the electrons have, kinetic energy. This kinetic energy will increase when the heater temperature increasing. By that, the collision between these electrons will be more. The distance between these atoms, between these electrons, will be more. After that, that's right, now we have a good group of electrons, it's enough, but these electrons can't reach the screen. By that, we can't read our results. We can't know what is the result. By that, we need acceleration process to can increase the velocity of these electrons to can reach the screen. By that, to can reach the accelerating process, we will use the anode and parallel and horizontal plates to decrease the velocity. By that, to accelerate the electron beam. By that, the electron beam can reach the screen, and the waves or lines will plotted like that. Cathode, like the diode experiment, it was the negatively terminal, and anode is the positively terminal. Here, the circuit, we will connect our devices according to the circuit. CRO device, voltmeter will connect horizontally with connect by this, not series, because it's not a meter. We connected it with the CRO, not with the power supply, to can determine, to can know the voltmeter, what is the different potential will pass from the CRO. Here it's horizontal connection, not series. And here R is the R state, it will be maximum. That's mean when I turn on the power supply at DC, specifically I will work at first at DC, no any current and voltage will pass because the R state is full at maximum. By that, it will act like a wall. Our work will depend on to decrease the R state little bit and take a look to the voltage, to the voltmeter, which result will be. Here, to note, it's important idea. What is the dot here? What is the line here? Why this line is horizontal, not perpendicular? That's evidence that means we work correctly on DC, not AC. Because if I worked on AC, the line will be horizontally, not like that. Will be, sorry, here it's horizontally line, will be across, will be like that. Perpendicular. Okay, the dot here, at first, to be sure my works, my results will be right, I must make this dot, that's mean the voltage, the voltmeter equals 0 volt, at the center. To be sure my results will be right, by somehow from these squares, I can manage this dot to be at the center between these two cross horizontal or perpendicular lines, to be at the center, to be sure my scalar is right, my CRO center is right. After that, turn on the line to be like that. Sure, we will deal with it just a green line or dots. Here, the main idea to this experiment to can determine the resistivity of the CRO at DC, I have two lines. Here, from the dot, after that line at the middle, that's mean my center is right. After that, from one bottom from them, I will push it to have a line up or down. After that, I will calculate the reverse, the deflection of this line, and manage and calculate the distance between them. Here, we have some cubics in the screen. That's to help us to can manage the distance between these lines. Every cubic equal 10 millimeter. That's mean 1 centimeter. Here at this picture, O and O dash, the first position and the deflection position, and the distance between O and O dash, it's D. Our job today, we have column contains from voltage, the readings of the voltmeter, and the distance between O and O dash, that's mean D, and its unit will be millimeter. Now the points O present what? Present the dot of CRO when the reading of the DC voltmeter equals 0. By using the R hesitate, will apply the DC voltage to the CRO because it was at maximum. That means no voltage will pass. And we know when I say DC, that means the current is constant because that we don't talk about it. The dot of light will move to new position on the screen. By that, measure the deflection on the screen. Our job to measure at first to increase the R hesitate, manage the voltage. I selected it to be 2, 4, 6 until 10 volts. After that, determine the distance between each situation. This is my column. This expected be our curve is expected to be like that. D distance at millimeter unit will be at y-axis and VDC will be at x-axis, and we will upload the line here. That's mean when I take a look to the curve like that, that's mean the relation between D and V is a linear relation, direct relation. When increase V or D, the another will increase too. Here, the slope will be sure, like I said before, delta D divided on delta V. Here, it's my column. We'll try to follow all of this. I expected the deflection distance will increase too, because at previous curve, at this curve, it was a linear relation between D and V. Here, it's important note, in my opinion, it's not necessary to repeat all of these steps. You can measure the sensitivity to CRO at AC. I will use this law, this function, to determine the deflection sensitivity of AC voltage by saying 2 root 2 multiple deflection sensitivity of DC voltage, what we will calculate now. After that, just dot in 2 root 2 to determine, to calculate the deflection sensitivity AC. Here, it's important note, when I work on AC, that will be good evidence to us. That means we work correctly because the line will be like that, not horizontally anymore, vertical. I will plot my curve depending on these readings. Here, the millimeter and the DC volt, I divided every 1 centime to equal 1 volt. By that, 10 centimes, that means 10 volts. It's easy. After that, I have 34. The maximum was 34. By that, I was thinking why we not put every half centime, every 5 millimeter to be 1 volt. That's be 2 volts. 2, 4, 6, 8, 10. That means 2 centime and half equal 10 millimeter. By that, 14. That's mean how much centime? 1, 2, 3 and half, because every half centime equal 1 millimeter. It's a good idea. By that, I reached the 33. Now let's calculate the slope. Delta D divided on delta D divided on delta V to be equal 3. And you can check another curve, another slope. I selected my slope to be dealing with 34, 22 at D and 10, 6 at V. You can change the slope by plotting another one. You can select these 2 points to be 22 minus 10 divided on 6 divided minus 2, the same result will appear, just equal 3. By that, when we were saying the sensitivity or deflection sensitivity of DC equal slope, that means will be 3, but slope without units. Here the sensitivity shown with unit. From where I take my units here from D divided on B, that's mean millimeter divided on volt. That's mean the sensitivity equal 3 millimeter divided on volt. Now let's calculate the sensitivity of AC will be 2 root 2 3 to be 6 root 2 millimeter divided on volt. That's it. Now let's discuss this curve. Here, the relation between V and D is linear or non-linear. Sure, it's not linear. That's mean directly or reverse relation. Sure, it's directly relation. That's mean when increase x-axis, y-axis will increase and reverse bias. I mean, when increase D, the V will decrease too. We don't have any exponential relation, don't have any increasing, rising in somewhere. That's it. See you in the next lecture. Next lecture, next experiment. Have a good day. See you good. Have a good time. Thank you for watching or listening. Have a good day. Oh.